Good morning, y'all. All right, we are continuing with our work, energy, and power unit. So, we have already talked about work, kinetic energy, and then our two types of potential energy. We had gravitational potential energy and elastic potential energy. So today is kind of an extension of elastic potential energy. So, Hooke's law, what we're talking about today, is about springs. All right, so Hooke's law has to do with springs and other things with elasticity. All right, so anything that stretches or compresses should follow Hooke's law. All right, so Hooke's law is just a law that gives the relationship between the force that's applied to an unstretched spring and then the amount that the spring is stretched. So, what it says is that the extension of a spring is directly proportional to the force that is exerted on it. All right, so we're going to be proving that in just a little bit. All right, now, not all springs, so think about like the springs in the spring scales that we've been using, or we're going to look at different springs later on. All right, so if you overstretch a spring, it will no longer follow Hooke's law. All right, so it's said to have reached its elastic limit, and that's whenever it permanently deforms. So if you have like a slinky or something and you have overstretched it, it's when you get that kind of space in there whenever it no longer returns to its original shape. All right, so we see this used, like people in the real world use Hooke's law. It's used with spring scales, right? Like whenever we measure weight in car suspensions. So those shock absorbers in clocks, the wheels, in engineering, whenever we're designing structures or materials, and even in instrumentation with pressure gauges. All right, so all of these things follow Hooke's law. All right, well, what is Hooke's law? All right, so Hooke's law, we do have an equation, and it just states that the elastic force, remember, elastic force and spring force are the exact same thing. Okay, so elastic force and spring force are used interchangeably. So if you want to say spring force instead of elastic force, you're more than welcome to. It is the exact same thing. All right, so your spring force is equal to negative kx. All right, so the other day we talked about our elastic potential energy. So that was 1/2 kx squared. So you see that we're using the same two variables, but in a lot different way. So elastic potential energy is half of the spring force constant times the distance that it was compressed or stretched squared. Here, we're not looking at the energy, we're just looking at the amount of force required to move it. All right, so that spring force is equal to negative kx. So that negative will always be there because your elastic or spring force is a restoring force. All right, it wants to bring that spring back to its original position. All right, the K is still your spring constant, so how strong or how flimsy a spring is. And then your X is going to be, did you fill it back up? Okay, so get one of those. All right, no, you're good. All right, so your X is just going to be the distance that it is either stretched or compressed. All right, so let's try this example. So if a spring has a spring constant of 0.5 newtons per meter, and it is stretched 0.5 meters, what is the force of the spring? All right, so we have been given our spring constant of 0.5 newtons per meter. All right, we have also been given X. Sorry. There we go. All right, so we've also been given the distance that it has been stretched, which is 0.5 meters. All right, I want to know what is the force of the spring. So what is that restoring spring force? All right, so we are looking for either, again, you can put it as F sub spring or as F elastic. It is the same thing. All right, so we are looking for our spring force. We know that the spring force is equal to negative kx. So again, that negative is there because that force is always opposing the motion, all right, the direction of the motion. So we have that negative times 0.5 times our distance that it was stretched, which was 0.5 meters. All right, so 0.5 times 0.5 is 0.25. So our spring force is negative 0.25 newtons. All right, that negative, again, force is a vector quantity, so that negative just tells us the direction that it is. Again, negative means it is a restoring force. It wants to go opposite the direction of the motion. All right, now this second one, we have a mass of 0.55 kilograms is attached to a vertical spring, stretches the spring 2 centimeters from its original resting position. I want to know what is the spring constant. All right, so to get an idea of what this looks like, we need to draw a free body diagram. So if we have a vertical spring, so think about a spring scale, we have our force of gravity pulling that mass down, and then we have our spring force that's pulling it back up. All right, so this is at equilibrium. All right, so that means that these forces are balanced. So we're given our mass of the spring, of the mass that's attached to the spring is 0.55 kilograms. And then we know that the distance that it was stretched, so that's our x, was 2 centimeters. All right, now big red flag should be going up in your head. Our distance is not measured in centimeters. It is measured in meters. So we divide that by 100 and we should get 0.02 meters. All right, now we know that we're looking for K. So we know that our elastic force or our spring force is equal to negative kx. We're solving for K. We have X, but we do not have that elastic or spring force. But what we do know is that the elastic or spring force is equal to our force of gravity, all right, the weight of that mass. So we know that Fg is equal to mg, so that's 0.55 times negative 9.81. So 0.55 times negative 9.81 does give us a negative 5.4 newtons. So our force that's been exerted is negative 5.4 newtons. That's equal to negative K times 0.02. All right, so we divide both sides by negative 0.02. Negative 0.02, that cancels that out. So K is going to be 270 newtons per meter. All right, now if you didn't remember to include the negative on that force, all right, then that's fine. You just have to remember that K can never be negative. K can never be negative. It is a spring constant. It's never going to be negative. All right, so if you don't remember to put that negative, it's fine. You just got to remember that K is a scalar quantity. All right, now, same spring. All right, so the same mass is used in this one. So a different spring, but the same mass. So same mass means that we have the same elastic or spring force that has been used. So that same negative 5.4 newtons. but it's replaced with a different spring that stretches a different amount. So X is going to be 36 centimeters. Remember that distance stretched is not measured in centimeters, but meters. We divide that by 100. That gives us 0.36 meters. And then we want to know what is the spring constant for this one. All right, so we know that our elastic or spring force is equal to negative kx. Solving for k, we divide both sides by negative x. So k is equal to negative 5.4 divided by negative 0.36. So we divide those two. We get a K, so a spring constant of 15 newtons per meter. All right, so that's what I asked you here. So the second part of that is this spring stiffer or more flimsy than the one before? And the answer is going to be more flimsy. It's less stiff. All right, and we can kind of look at the situation. All right, so if we are attaching the same mass to both of these springs, the first spring only moved 2 centimeters. This spring moved 36 centimeters. So that tells us that this spring is definitely more flimsy, less stiff because it moved further. All right, and then we have our last one. This is kind of proving Hooke's law, all right, that relationship. So let's look at this one. So we know that a force of 16 newtons is required to stretch a certain spring a distance of 40 centimeters from its rest position. All right, so we want to know what force is required to stretch the same spring twice the distance, 3 times the distance, and then half of the distance. All right, so we're looking for the elastic force for each of these. All right, so we are looking for what force is required to stretch these. So if our original distance was 40 centimeters, twice the distance is going to be 80 centimeters. 3 times the distance is going to be 120 centimeters. Half the distance is going to be 20 centimeters. All right, but for us to know or to finish the equation, remember F elastic is equal to negative kx. We know the x, but we do not know the k. We don't know the spring constant of this particular spring. So that's the first thing that we have to solve for. All right, so we have to find K for this specific spring. All right, so I told you that this was the force that was required, and this was the distance it was stretched. So we know that the elastic force is equal to negative kx. So K is what we're solving for. We divide both sides by negative x. So K is equal to negative 16. Remember, the force is always going to be negative because it's a restoring force, divided by negative 0.4. All right, the reason that it's 0.4 instead of 40 is because this is 40 centimeters. So we have to divide that by 100. That gives us 0.4 meters. So negative 16 divided by 0.4 does give us a spring constant of 40 newtons per meter. So we're using the same spring with the same spring constant the entire time. So F elastic is negative kx. That's going to be negative times 40 times twice the distance. So we started with 40. This one's going to be 80. So that's 0.8. All right, this one is negative kx again, negative kx again. So we have negative times 40 times 3 times the distance. That's going to be 120 centimeters. Divide that by 100. That's going to be 1.2 meters. So that gives us our last one, negative 40 times half the distance, which is going to be 0.2 meters. All right, we plug all of these in. The force required to move it twice the distance is going to be negative 32 newtons. All right, the force required to move it 3 times the distance is negative 48 newtons. And then the force required to move it half the distance is negative 8 newtons. All right, so let's look at that. So 16 was our original force, 40 was our original distance. So compare those two forces. We moved it twice the distance. We had to use twice the force. So if you're moving it twice the distance, it's going to require twice the force. If you move it 3 times the distance, that requires 3 times the force. If you move it half the distance, that requires half the force. All right, so up here we mentioned that the extension of a spring is directly proportional to the force exerted on it. We mentioned that up here, so they are directly related. We are seeing that here too. All right, so we half the force, half the distance. We want to double the distance, we have to double the force. All right, so force and distance are directly related. All right, so this is not going to be on your quiz, but it will be on your test. So again, if you don't understand something, you know where to find me. Y'all have a good one.